Good evening, everyone. Welcome to the first workshop where we will be going over a short introduction to computers. By short, I actually mean I feel like this might go a bit over an hour, so just a heads up, it is pretty informative, but I'll do my best to guide you through. My name is Adam. I'm the head instructor for Rutgers Cybersecurity, and hopefully you'll enjoy. First, we'll go over what we're going over today. We're going to start off with a short introduction on early computing, more specifically the first computers, which were punch card computers. After that, we'll talk about what is an operating system and then its functions. After that, we'll look at the different parts of an operating system, the drivers, the kernel. Then we'll take a look at two of the most popular operating systems, Linux and Windows, and see what they have to offer. So let's get started with the early history of computing. The first computers were computers. Here's exactly how people programmed with punch cards. The ancient programmer back in the day didn't write C or Java. They wrote in machine code, which is exactly what the computer sees. This basically means that programmers had manual control over exactly what the CPU was doing and the I/O interactions. Some newer punch card machines, you could write Fortran or even COBOL, but the first ones used raw assembly. To write a program for a computer, you had to know the exact hardware specifications, what signals would trigger a print, and etc. You had to know the exact hardware knowledge. You had to have the specifications for not just the machine, but also the devices. This means that your programs were typically tailored to a single system, and because each computer has its squirts, most programs were written to support only the computer they had, along with its I/O. Afterwards, you'd have one instruction per card. Each machine code instruction was punched and labeled on a single punch card. And if you wanted an entire program, you need many cards. In the GIF here, you can see about right now, there's a giant stack of punch cards with a 3/2. That is that is one of the programs. I know that for the program that sent humanity to the moon, that was well over 100,000 punch cards. So it adds up pretty quickly. One benefit of using punch cards is if you want to reuse code, you can just reuse the cards. If you have, for example, a matrix multiplication algorithm, you could just reuse the cards which do the operation. You put the inputs and outputs, and you get your output. If you want to actually run the program, you would first load the cards in the queue, and then the computer would read and execute the instructions one card at a time, whatever is there, regardless if it's correct or incorrect. The computer does not care. Once it's finished, once the program is actually finished, you can take back your cards and the output is generated. You can also take the output. Do you guys notice any problems?
I think it's too tedious and there are so many cards to maintain.
Yep, that's part of it. Having so many cards could make it very easy to, for example, misplace or misorder the cards. What people would do is they would have a big slash so you could order the cards correctly. But even then, if you lose a card, you'd have to rewrite it. Anyone else have any ideas? Well, other than the obvious of using punch cards, of misplacing and ordering them, another issue would be having to manually load all the cards into the program. That takes time, and you need a dedicated person. And typically, companies would have a dedicated person just loading and unloading the programs into the computer. Another issue is due to the sequential nature of the early punch card machines, you could only have one program run at a time maximum. If you wanted to run your second program, you would have to wait until the queue finishes, until the program before you finishes, before you could put in your own program. Additionally, the physical punch card, using physical punch cards as inputs is very slow. Even if the computer could read them at light speed, you still have to move the punch cards in and out of the scanner, which takes time. Because of this, it's safe to assume that the punch card computer actually didn't spend much time doing its computing and mostly waited for I/O, or basically reading in the punch cards or printing out to a printer. And obviously there's the time where you have to wait until loading a new program. Another issue which made programming with punch card computers very difficult is that programmers had to have the knowledge of the hardware specs, not just the computer, but also the peripherals and how they interact together. For example, one easy example would be trying to print hello world. It might seem simple. You could just, in Python, it's one line. But, but back in the day, you'd have to account for different ways a printer or printers could print to the screen. This means that to write for a punch card machine, people had to spend time learning to wrestle with the machine before they could actually write useful code. It's the onboarding time which makes it very expensive. Additionally, since programmers usually only worked at a single machine, a guard stack only worked with a single machine. Let's say you did successfully write your Hello World program. It's not very likely that it's going to work on a different punch card machine. Another issue which some of you programmers out here might understand is debugging. If you understand how hard debugging is, imagine how hard it was back in the day with punch card computers. The computer didn't give you any error messages. All the computer did was execute exactly what you told it to. So if a program failed or gave the wrong answer, you had to figure out why the program didn't work outside by looking at the inputs and the outputs. It didn't highlight you the magic line or where the program messed up. Basically, the responsibility was on the programmer to write good code. So what was the solution to all of this? Well, I'm glad you asked. We're going to be talking now about what is actually the operating system. The operating system replaced the punch card machine. Essentially, it's a program that always runs on your computer, and it basically handles everything. To solve the operational problem, the operating system was created. It doesn't manage just the physical components, for example, CPU, memory, but also it's responsible for keeping all the other programs in check, programs that you run. It basically acts as an intermediary between a user, programs, and hardware. It does a lot of stuff simultaneously. Some of it is program management, which basically is starting and stopping programs, memory management, which is one part of the hardware, file system management, making sure program files are kept, device and I/O management, such as making sure two devices are using the same I/O, network management, which is communicating with other computers, authentication and security. This mostly focuses on hardware integrity, but nevertheless, the operating system also handles a bit of security. And last but not least, it provides the user with a system level CLI and GUI, which stand for Command Line Interface and Graphical User Interface, respectively. So here are the different software components that make up an operating system. First off, we have drivers. The drivers are binaries which tell the OS how to interact with the different hardware components. You may know this as graphics drivers, audio drivers, network drivers, USB or keyboard, or other controller devices, but it's not restricted to just those. The hardware drivers, they sit between the kernel and the actual hardware. They provide an intermediary and define how the actual hardware is and what are the functionalities. The drivers also could enable extra hardware functionality by telling the kernel the functionality. For example, one thing that you guys might be familiar with would be screen resolution, GPU memory, and whether hardware acceleration is possible. Next up is the kernel, which is the core of the operating system. The kernel is the heart and soul of any operating system. What it does is it manages the machine's resources to other programs that you might want to run. It basically is between the software and the hardware. If a software program needs some resource, for example memory, the kernel would be there to allocate it and make sure the system is running fine. It also manages time sharing of the CPU, which is basically allowing multiple programs to use the CPU at once, allocating memory, and lets programs use I/O, for example, screen or keyboard input. Some popular kernels that you may or may have not heard of are the Linux kernel and the NT kernel, which is used in Windows, and we'll get into that a bit later. If anyone has any questions, feel free to stop me. I'll be glad to explain. Anyways, the shell is what separates the user from the kernel. It's the medium which you communicate through with the operating system. What it really does, in that sense, is interpret the user commands. If you want to do something with the kernel, you have to do it through the shell. There's really no other way, unless you write a program. Shell, it interprets whatever commands you input, for example, as system calls, and then it gives those system calls to the kernel and lets it process it. One way you could think of it is think of the shell as a literal shell around the kernel. It basically protects it from all sides, only allowing a few entrances in. For example, like in a turtle shell, there's openings for the legs and the head and the tail. The shell, it can be a command line interface, which is known as a CLI, or it could be a graphical user interface. The CLI lets the user specify exactly what they want to do by typing the correct command. If they want to edit a file, there's a command to do that. Alternatively, it could be a graphical user interface or a graphical shell. This offers a more intuitive interface. Everyone knows how to use Windows, I'm pretty sure. But naturally, designing a graphical user interface is much more complex. You need a lot more working parts. Some functionality you might need is drag and drop, resizing, clicking, selecting, etc. Last but not least, we have utilities. And these are basically any programs that you might want to run. They're also known as user space tools, and like I said, they're user programs which aren't part of the kernel, they're outside of it. Anything that you run, whether it is Zoom or Discord or your browser, that's a utility. What these utilities do, they simplify and make easier to use common tasks. Common tasks like, for example, web browsing or watching a YouTube video. These utilities, they're typically ran by the user from the shell, which is outside the kernel. And yeah, utilities can pretty much be anything, from even simple shell commands like in Linux, or they can be entire desktop environments, such as KDE on Linux. In the top right, we have a graphic which illustrates where each of these components are located. The hardware is the center. This is basically your physical motherboard, your RAM, your GPU, etc., etc. Around it are the drivers, and each driver is responsible for one part of the hardware. The kernel then communicates through the drivers with the hardware. It also communicates with the shell to the user, which then runs your utilities. Next, we'll talk about one part of the kernel of the operating system functions, which is process management. There might be a lot here, but it's pretty simple. One part is process management. This basically ensures that processes are executed correctly, they terminate quietly without issues, and that they're allocated and deallocated resources. So what a process in a computer is, it's actually a program, but in execution. A program is passive data in memory. It doesn't do anything. But a process is active. It's an active entity, and it's being processed by the system, and it's being executed by the hardware. As you might know, you can have many processes spawn from just a single program. When the user wants to execute a program, the kernel has to first allocate resources and spawn a process. They need to allocate it with, for example, PID, which is a process ID number, and resource, for example, memory, and giving it a CPU thread. What the kernel also does is manage parent and child relationships between processes. And when a program is done, it then can free the memory when it exits. Upon termination, whether it is by the program exiting successfully or if the program is terminated externally, then all of the resources are then freed and then can be used by other processes in the system. Deadlock handling is an issue which arises when you have multiple processes that need the same resources and they're fighting over. Deadlock specifically is when two or more programs they can't continue because they need someone else to release the resources that they need to continue. Some common deadlocks could occur with memory, I/O, or graphics. Think about it. Your browser might need to take up a certain space on the monitor, and your desktop environment as well needs to display pings and notifications. If you have a deadlock, you're not able to use the screen, which sucks. And that's why it's very important for the kernel to be able to detect deadlocks and handle them correctly. Deadlock needs exactly 4 conditions to occur. First of which is mutual exclusion, which is when the programs both need to access a resource which is exclusive only to one program. For example, if you have a file that can be written to, you can't have two people writing to the same file, which that would be an example of a non-shareable resource. Second condition is hold and wait. This is when two programs they're holding certain resources, but at the same time they're still waiting for something else to be freed. The third condition is no preemption, which in simple terms means when resources can't be taken away once they are given. So for example, if you give memory to a program, that memory can't be freed. If you give a program access to graphics, you can't take it away. That would be no preemption. And circular wait is when you have a cycle of two or more processes. They're each waiting for a resource which is held by the next process. So in the graphic below, we have the resource 1 and resource 2, which both are needed by processes 1 and 2. Process 1 in this case has resource 2, and process 1 already has resource 1, and process 2 already has resource 2 allocated to it. Now process 2 is waiting for resource 1 to be freed, but it can't be freed because process 1 can't give it up. And same thing with the second resource, and that's what we call a deadlock. Another way you could think about this, here's an analogy. Alice and Bob, they're both making burgers for themselves. It's 4th of July weekend, and they're having a barbecue party. They're almost done making the burgers, and now they want to get the burgers to eat them. Alice has a spatula, and Bob has the actual grill with the burgers. Bob's the one grilling here. They both need the spatula and the grill to pick up their patty, but none of them can pick up the patty. Alice is waiting for Bob to give up the grill, and Bob is waiting for Alice to give up the spatula. And so they're waiting for eternity or until the burger patty is burned up. So that might be an issue. Deadlocks they're they're preventing people from eating burgers. How can we prevent this? Well, there's 3 main ways of handling deadlocks. The first one is prevention. Basically making sure that there's no possible situation where a deadlock can occur. To do this, we could just basically make sure the 4 conditions don't happen. So we could have at most 3 out of 4 deadlock conditions satisfied, but not the 4th one. One way is to stop, hold, and wait. So if a program needs a resource, they must first release everything that they have. So they can't hold and wait. If they're waiting for a resource, they need to release everything and then grab all the resources again. Or another way you could do this is if you know you're going to require a certain resource, you can request that resource ahead of time. That way the kernel has time to allocate the resource to the program. Another way of deadlock Another method of deadlock prevention would be no preemption. So this basically means a program can release the resources once it's done using them. So if it's waiting for a required resource, if it's waiting for something, it should release its resources one by one and then wait until everything is free. That way, if for example Alice needs needs Bob's grill, she must first give up her spatula and then get and then get both. This prevents the deadlock and both can eat their burger happily. Third method of deadlock prevention would be circular wait, which this basically means this is a bit more complicated. I'll try to explain it briefly. To prevent deadlocks by preventing circular wait, you simply assign resources, you number the resources, and you order them. Then a process can only request resources in an increasing order. So once you request resource 1, you can only request resources higher than 1. Once you request resource 100, you can request resources at least 101, and so on and so forth. In this way, requests cannot form a loop on the number line since you can't have 1 less than 10, which is less than 1. That never occurs. And with that, you can prevent deadlocks. Second method would be deadlock avoidance. So if a situation arises where a deadlock can occur, you can basically avoid the deadlock. The operating system would enact certain measures. Think, for example, if you're driving along a highway and you notice that there's traffic, there's congestion. This would be like taking an exit to avoid the traffic. And some algorithms that could be used for that would be Baker's algorithm. This is outside the scope of this presentation. If you're interested, you can learn more about it. And the third method would be deadlock recovery, which is really only used in real-time operating systems, or RTOS. So I won't be going over this. Finally, we have process scheduling. Processes can be in one of 5 states. They can be start, they can be ready, in state ready, they could be running, or they could be in start wait, or terminated. All programs start in the start state, and when the program has all its resources allocated, all its initial resources allocated, it enters the ready state. And then once it's ready, the kernel can take any ready programs and set them to the running state by executing them. After it executes in certain lines, it can then wait, and then once it's done waiting, it can go back to ready, and when the program is finished, it can be terminated. Again, scheduling is important because each core can only execute one thing at a time. So the scheduler basically manages all of these and basically ensures that the CPU is used up as much as possible. Next up is memory management. Who here loves memory? Memory, as you probably know, is very valuable in a computer, especially nowadays, and the operating system uses several methods to make sure that memory is used up in the most efficient manner. First off, we have virtual memory. Essentially, what the kernel does is it acts as an intermediary between the program's memory and the physical memory. As far as each program is concerned, they are the only ones with memory, and they can't overwrite the memory of other programs. It's physically impossible. There's a circuit on the motherboard, which is called the Memory Management Unit, also known as the MMU, and that translates the program's memory address into physical addresses on the RAM. and the MMU decides what addresses are allocated to each program. Having program memory isolated from the physical memory, that allows the OS to physically address the memory how it sees fit, which is basically most efficiently. The OS can allocate the memory by using it up. It can use it sequentially, or it could do it in such a manner which prevents fragmentation. And this simplifies memory management for programs since all they see is linear memory. Another reason why this is important is because of an old security vulnerability. Back in the day in older operating systems, originally all programs had access to physical memory. They all had the same access from byte 0 to the last byte. Could anyone think of why this would be an issue if everyone could read the same memory? If you can't speak, if you could type it in the chat, that'd be great.
I guess so that stuff doesn't get overwritten in memory.
Yep, that's a good point. If you have two or more programs, they have access to the same memory space. Let's say one programmer prefers to have a certain chunk of memory, let's say from byte 100 to 120. They have no idea of knowing what bytes other programs might want to use. So programs could arbitrarily write memory, and back in the day, there certain operating system core functions were also in memory, and programs were able to overwrite that. In other words, bad programs, they could read or write memory of other programs. That's a big issue because even system memory was part of it, and that could just cause undefined behavior that could crash or corrupt your machine. Depending on the exact attack, it could also exfiltrate your entire system. So having virtual memory allocated to each program, it makes it simpler for everyone. The operating system can efficiently manage the memory, and each program doesn't have to worry about other programs. They just see their contiguous block of memory. They don't have to worry about fragmentation, so on and so forth. And having the virtual memory, it solves the fragmentation, which, if you don't know, it's an issue arises when you use unfree memory. We have an infographic on the bottom right. Each program can have view space, has its own assigned space, and they can use the space or have it not used. If they don't use all of their space that they're allocated, you could say that there is internal fragmentation. But once a program leaves memory, then that memory is free, and whatever memory is around it could still be assigned. So when programs leave and exit memory, you have external fragmentation. What this does is if you have a program that requires 1 gigabyte of memory, and you could have that memory available on your hardware, but there's no 1 gigabyte contiguous block of memory which you could use, which means you can't run the program. So solving fragmentation means you could run more programs with the same amount of memory. Another part of memory management would be paging. What this does is it's another way of drastically increasing the efficiency of memory. So what the operating system does is it segments memory into 4 kilobyte blocks or pages. They're called pages. And when the operating system allocates memory to a program, it does so using, for example, n pages. Instead of using raw bytes. The program receives these pages as frames, so that's what a frame pointer is. It's basically the pointer to your page. What this does is it reduces the amount of indexing bits, or the address bits which you need to index the memory. So, for example, let's suppose hypothetically that 4K is, for example, 256 bytes. I know that's not the case, but imagine that's 2 to the 8 for a page, hypothetically. 2 to the 8 bytes. I bet the numbers are wrong, but you save 7 bytes by having a page instead of addressing by bytes. This also helps solve external fragmentation because instead of trying to fit memory into bytes, which are very small, the units are pages, which are much larger. And programs are much more likely to fit into the 4 kilobyte page. So there's fewer offsets and a bit less external fragmentation. Obviously, there is still some, but in the back end, the operating system handles it. But one issue that this does cause is it increases internal fragmentation, which is when the programs don't use all of the 4K bytes inside their pages that they're allocated. This issue can't really be resolved by the operating system. These have to be solved by the individual programs, and that is through good memory etiquette. You request memory only when you need it, and when you're done with the memory, you then free it once you're done. Another good benefit of paging is having common libraries in shared pages. Common libraries such as C libraries can be used by many programs as dependencies, and having them linked to a shared page drastically decreases the amount of memory needed since you reduce duplicates. If you have, for example, one common library would be to print to the screen hello. So if you have multiple programs which repeatedly print something to the screen, having the shared library reduces the size of the program since there is one authoritative copy. By removing the duplicates, you can have more programs run on your machine at a time. Another part of memory management would be memory allocation. As mentioned before, the operating system, and specifically the kernel, is responsible for allocating all the resources, including the memory, to the programs and processes. Like mentioned before in the process management slide, they allocate the initial memory to load the program and to start it. And afterwards, when a program is running, the program can request additional memory, and when it does so, the operating system can dynamically allocate more chunks of memory to the program. And when the program eventually frees the memory, for example, when it doesn't need the memory anymore, or when it is terminated, the kernel then takes back the resources and it frees them, letting them to be used by other programs. If a program requests, for example, too much memory, the operating system can just say, no, what are you trying to do with this? And it also handles certain security cases like that. Finally, we have memory hierarchy. The operating system, which I've said over and over, it's responsible for managing memory. The operating system doesn't just try to allocate the memory, but it also tries to prioritize memory because not all memory is created equal. To illustrate this, we have the memory pyramid, which is pictured on the slide. In the top, we have the CPU registers. These are very close to the CPU and the closest you can get, and these are blazingly fast. There's not a lot of them. There's probably around 1632. It depends on the exact architecture, but there's a few registers, and they provide a quick storage for certain bytes, and you can read and write very quickly to them within a few CPU cycles. It's very fast. Below that is L1, L2, and L3 cache. Those are grouped together, but L1 would be the fastest and the closest cache to the actual CPU. Next is L2 and L3. The difference between those is pretty much speed and size. L3 cache is larger than L2 cache, which is larger than L1 cache. These are also very fast, and they're larger than registers, and lots of common procedures are or cache in the L1, L2, L3 cache for very quick access. Below that is probably the most well-known category, which is RAM, probably because of prices. What RAM does, it provides relatively quick storage to more bytes when you're executing. This is what most people think of as memory. However, the reason why RAM is called volatile memory is because when you turn off your computer, the bytes stored in memory are lost, they're turned off. So that's why RAM is volatile. It requires a power source. If you do need to store data, even with a power surge, you do those through persistent disk storage, which is your SSDs and your hard drives. These are slower than RAM by orders of magnitude, but you do have that stability and security of knowing your data is there. In the old days, between the punch cards and hard drives, people used magnetic tape drives, and compared to SSDs and hard drives, they have much better long-term data integrity, which is why some companies actually make backups to magnetic tapes. But as you can imagine, they were replaced due to how slow they are to read and write, even compared to hard drives. In modern operating systems, for example in Linux, you could use your actual persistent disk storage as memory through what is called swap. Swap memory exists on your actual hard drive. In my system, I have around 4 gigabytes allocated swap. And what that does is, if you run out of RAM or volatile memory, the operating system is going to go to the next fastest option, which would be your hard drive. So the operating system, simply put, the reason why we care about memory hierarchy is the operating system wants to put as much memory as fast as possible. So it tries to allocate as much memory as it can to the top and then slowly fill up the bottom rows. Next up, the most exciting part, Linux versus Windows. Can I get a poll here? How many people here use Linux and how many people use Windows? Madox, you use Linux. I assume everyone else uses Windows. That's fine, but you guys are kind of missing out on the benefits of Linux. And I'll go over briefly what I mean by that. As we all know, Linux is created by this random guy called Linus Torvalds. He initially created it in 1991 as a small hobby project. The story of Linux is well known. You can read about it online, so I'm not going to go too much into that. But before this, Richard Stallman, that's the guy you see here hugging the laptop, he started the GNU project, and his mission was to create a fully open source operating system. At the time, he had everything except for the kernel, which he wanted to call the GNU herd kernel. They're still developing that, but Linus made his own, and it worked well enough, and it was compatible with Unix, so they used that. GNU at the time made the core utils, which would be like the shell programs or shell commands. They also made a C compiler, which we now know as GCC, the GNU debugger, GDB, and lots more programs. The GNU utilities are used pretty much everywhere, and not just because they're good, but because they're free. Anyone can download them, anyone can use them, and because of that, they're on pretty much almost every system in the world. They're in most production servers, but they're not everywhere. Some exceptions would include, for example, BusyBox, which is a different rewrite of the GNU utils, and obviously Windows. Windows doesn't have the GNU utils unless you install GDB, which in that case you're running GNU code. Currently, there's hundreds of distributions of GNU/Linux. I will call it that. There is a copy pasta, and what it basically is trying to say, the copy pasta, is that Linux is the kernel. It's the core part of the operating system. And as I mentioned before, the kernel is the program that allocates the machine's resources to the programs that you run. GNU people who really love GNU, they would say that Linux is important, but in reality, Linux, being the kernel, it's basically the key. It's the heart of your Linux operating system, and it holds everything together. One fun fact about the Linux kernel is that it's monolithic. What that means is that it's a giant program, and all of it runs in user space, in the kernel space. This was intentionally chosen because the monolithic kernel would be very easy to develop, and surprisingly, it also helps improve performance since there's less overhead as opposed to a hybrid kernel. However, a problem with a monolithic kernel, which you may be exploiting, would be that if any one part of the kernel is compromised, no matter what it is, the whole system is too. The whole kernel is compromised, which is why protecting the Linux kernel is very important. Another quirk of the Linux kernel is that it uses kernel modules which can be loaded at runtime. There's certain modules which you can start and stop. And the Linux kernel, this is maintained by it's developed by people all around the world, but they communicate through the Linux kernel mailing list, which is LKML for short. Linus Torvalds no longer writes the code. Right now, he basically greenlights any contributions to the kernel. He checks all the commits and greenlights them if they're good or bad. Some philosophy about Linux. Linux follows the Unix design philosophy, which, to put it simply, is keep it simple, stupid. Instead of writing complicated programs, you want to write simple programs which do one thing and do it very well. You have one function, for example, to allocate memory. And if you have lots of things you need to do, you would separate your different concerns into different parts. Keep everything short and simple. Another part of Unix design philosophy is to design your program and expect that it's going to interact with other programs. If you use Linux, which we'll be learning Linux in a few workshops, what we'll be doing is we'll be using different commands. And one good thing about the Unix design philosophy is you can pipe and you can combine different programs in ways you couldn't think of. Again, you want to write clear programs. Try not to use complex tricks. Try not to use complex algorithms. If there's a clever way of doing it, don't do it. Just keep it simple. And if there are optimizations, try to study them before actually using those optimizations. In short, the Unix design principles, they're intended to make it very easy to debug and save programmer time. They also are there to make it very easy for others to use and interact with the programs. Also, Linux is file-based. Everything is a file. When we get into Linux, you'll see exactly what I mean. But one example I could think of off the top of my head is that all of the user configs are stored in files or in a config directory. There is a file which manages all your users in Linux. And there's a file which manages your firewall rules. All programs in Linux are actually files, and even folders themselves are files. Surprisingly, even devices in Linux are files, but these are special kinds of files which normally don't read and write to. What are devices? Well, if you do a bit of C programming, you might have heard of standard in, standard out, and standard error. These in Linux are located in /dev/standard in, /dev/standard out, and so on. So everything in Linux is a file. Now the final key part of Unix philosophy and the philosophy of Linux is open source. Open source basically means the code can be read, copied, and modified by pretty much anyone in the world. Anyone in the world can read the original code for the Linux kernel. They can look at it, they can use it to learn, or write their own kernel from it. It doesn't matter. Anyone can look at it. They can also compile the code, they can study how it works, and if they find a bug, well, they're more than welcome to edit the code and share their contributions with other people. Because at the end of the day, if you have an issue, there's likely someone else in the world that has the same issue as you. Open source it's not just free as in like free as in beer. It doesn't mean that this program is $0. It's more than that. It's libre. It's not just you could see the source code. You can do pretty much anything with it, that's the philosophy of open source. The Linux file system, like I mentioned, everything is a file, but there is order to it. The file system is a tree with a single root. We'll go over a bit on how that looks in our Linux workshop, but some common file systems, they're ext4, ZFS, and btreefs. And additionally, I would also like to mention that you can have mount points or mount other drives basically anywhere in the system. So you can nest it in a million subfolders and you can have your mount point there. You could have your external USB mounted there if you really want to. Next up is Windows. Windows was developed by Microsoft, and the first iteration was MS-DOS, which stands for Microsoft Disk Operating System. It came in an actual physical disk, and you would load it, and that would be your operating system. Nowadays, Windows is the most common operating system in desktop operating system in the world. If you're alive, you've probably interacted with Windows. You have seen the blue screen of death and you've logged in. The Windows kernel, it's not Linux kernel, obviously. It's the Windows NT kernel. And that's what powers Windows. The NT kernel is a hybrid kernel, which combines aspects of your monolithic kernel, like Linux, and a microkernel, which segments pretty much everything. The hybrid kernel attempts to combine the best of both worlds. In Windows, the file system, you guys know how it works. Again, it follows a tree structure. However, all the different drives, they have their own labeled root. So, for example, you have your C drive, your D drive, and F drive for your external, for example. And for Windows, the most common file systems are the FAT, which is for older systems, that's a legacy file system, NTFS, which is most common nowadays, and exFAT, which is used for removable storage. Windows design philosophy. Using Windows is basically using APIs. Unlike Linux, where everything is a file, everything is an API. What do I mean by that? What I mean is the commands in Windows, they're structured as API calls. If you know JavaScript, you know what I mean. And another reason why I say Windows is APIs is the Windows registry. What the Windows registry is basically a database of all of your system settings. Everything is stored in that database. It's not a file. Although technically it is stored, but you have to interact with it through a database. Windows, unlike Linux, is proprietary. What this means is that development can only be done by those employed by Microsoft. Windows is intellectual property of Microsoft, which means they're the only people who can decide who can read, write, or modify or share Windows with other people. This might suck, but there are actually some benefits to closed source, which aren't many as opposed to open source, but there are some. One benefit is that not everyone can submit code. However, at the same time, one downside of of proprietary software is not everyone can submit code. What do I mean by this? Let's say you have a malicious actor who wants to put a backdoor in your program. I am totally not referencing the exe backdoor. Yes, I am referencing the exe backdoor. In a proprietary system, if you restrict access to only certain people, obviously you have to do some trust beforehand, but you know that only those people are editing the code. You can't have some random mumbo jumbo change your code and ruin your program. Another benefit of proprietary software is it gives developers an incentive to do well because they're paid by the company. Instead of open source devs working out of their own goodwill, the company with proprietary software can pay developers to write the code, and theoretically, it would incentivize developers to write better code. However, one big downside of proprietary is not everyone can contribute, and it makes it very hard for other people. What I'm thinking about by this is Nightmare Eclipse. Nightmare Eclipse is a security researcher who found several bugs in the Windows kernel. He attempted to report it to Microsoft, and they ignored him. They ignored him because he sent out entries to the bug bounty program. And these were actually high severity vulnerabilities in Windows. They ignored him, but several months later, they patched those exact vulnerabilities in a Patch Tuesday update, not even referencing him. So naturally, he felt obligated to bully Windows. Another philosophy of Microsoft is compatibility. It's not just making sure that any system can run the operating system. Windows is made to be backwards compatible. It takes all the old standards and attempts to fit them all along with the new standards. This can be good, for example, if you want a one size fits all, but all these standards add up and they could be holding back performance and your security. Because older standards, they might be insecure and they might be also slower, which is why we have newer standards and newer methods. Current versions of Windows, they have accumulated tons of costs from supporting the older versions and from developing from those older versions. Promise this is the end. So just to recap, the operating system, it's a software in the computer that basically manages all the hardware and making sure it is used in the most efficient manner. It has lots of different responsibilities it has to handle, but it does it well, and we don't think our operating system's enough. Second most important thing is the kernel. This allocates all the machine's resources to the other programs that you run. It balances hardware, software, and the user. One key part about Linux is that it's open source. It uses the Linux kernel and ext4 and Btrfs file systems. And for Windows, it's not open source, it's proprietary. It uses the NT kernel and it uses control panel utilities, and you can edit stuff through the Windows registry, and it uses the FAT and NTFS file systems. That's pretty much it for me. If you do want to learn more, there's plenty of online resources. I use some of these links. I use all of these links actually to research for these slides, and there's countless other forums online. If you do want to learn more about operating systems, and there's several courses offered at Rutgers in the CS and ECE department. There's CompArch, operating systems, and again, thank you for being here. I'd appreciate it if you could give me feedback. And I'll post a link in the chat so you guys can also fill out the form. Again, thank you for being here and for paying attention. let me know if you have any questions, if you're interested in any different part of the operating system. I'd love to hear what you guys think.
Thank you.
Yeah, no worries.
Or actually, I think I had just one question. Like, I think when you were explaining about the kernels, just like
Mhm.
what exactly did it mean for it to be monolithic?
If it's monolithic, it means that the entire kernel is running in kernel space. There's in a kernel there's different modules which run, which for example manage your I/O, which manage memory, stuff like that. Certain parts need the kernel permissions, certain parts don't. So having everything in the kernel space is what actually makes a kernel monolithic.
Okay, thank you.
Yep, no worries. Anything else?
Nope. Have a good night.
Yep, good night. See you next week.